In this video, we're going to take a look at some examples of calculations for equilibrium, your equilibrium constant, and working to try and find the concentrations of your reactants or your products. This first example is from the Examcraft mock in 2020, and we're just going to focus on part C and D of this question. Okay, so first part we're asked about the equilibrium constant is to just write the equilibrium constant. So Kc is equal to the concentration of your products, so that's NH3, so that's ammonia. That's squared because you have that 2 before it. And underneath the line then you have the concentration of your reactants, okay, and you have to have them square brackets. Otherwise, you will not get your marks for writing your equilibrium constant, as them square brackets represent the concentrations of each of them. The next part of your question then, in an experiment, 4.5 moles of nitrogen and 13.5 moles of hydrogen were mixed in a 2 litre vessel at a certain temperature. It was found that 3 moles of ammonia in the equilibrium mixture. Calculate the concentration of each gas at equilibrium in moles per litre and calculate the value of the equilibrium constant Kc at this temperature. Okay, so first of all we'll write the information that we do know. We can write this in our what we call ice tables. So we have nitrogen, we have hydrogen, and we have ammonia. Okay, so we can go I for initial, C for change, E for equilibrium. Okay, so initially we have 4.5 moles of nitrogen and 13.5 moles of hydrogen. Okay, that should work out anyway because these are in a 1:3 ratio. And 3 times 4.5 is 13.5. So even if you were only given the concentration of, or the amount of moles of either of these, you should be able to work out what the other one is. Over here then, this is initially, so this is at time 0, so over here you don't have any ammonia formed as of yet. Okay, it was found then at equilibrium that there were 3 moles of ammonia in the mixture. Okay, so down here at equilibrium for ammonia, we have 3 moles. Okay, we started with 0, we now have 3 moles, so this change here is plus 3 moles. Now usually we would assign a substitute for an unknown such as x, so we can do this for this one as well. In this case though, you know that it's 2x because you have this 2 here. So we have that 2x is equal to 3 moles. So that means that x is equal to 1.5 moles. For our change for the other, for nitrogen and hydrogen, alright, here you're going to have minus 3x, that 3, because of that 3 there in front of the hydrogen, and here you're just going to have minus x. These are our reactants, that's why they're reducing, they're being lost. Okay, so if we know that x is 1.5, this change here at equilibrium you're going to have 4.5, take away 1.5. So again here you're going to have 3 moles. And here you're going to have 13.5. Take away 4.5. So here you're going to have 9 moles. So now we have the number of moles of each that we have, but these aren't our concentrations because it says in our question that it was in a 2 litre container. So we now need to divide those mole figures by 2 in order to get our concentrations. So all of these over 2. So that's going to turn out to be 1.5 moles per litre, 4.5 moles per litre, and 1.5 moles per litre. So then we want to calculate our Kc figure. So that's just subbing those figures then into our formula. Okay, so we have up here we have our formula that we're going to be subbing into. So on top we're going to have 1.5 squared, and underneath then we have 1.5 and 4.5 cubed, and that gives you a final answer of 0.01646, and that is your value for Kc. Now we'll go on to our next example, just down here. Okay, so bromine monochloride dissociated on heating according to the equation 2BrCl goes to Br2 plus Cl2. Okay, in an experiment, 0.9 moles of BrCl were heated in a 5 litre container at a certain temperature until equilibrium was established. The amount of free chlorine in the mixture was found to be 0.4 moles. So that's going to be your chlorine figure at equilibrium. Okay, so write the equilibrium constant for this reaction. Okay, so Kc is going to be Br2 Cl2 BrCl squared. Okay, so that's your Kc. That's your expression for Kc. Then calculate the value of the equilibrium constant for the reaction at this temperature. Okay, so we're going to use this table. So your initial change in equilibrium. So we have BrCl, we have Br2 and Cl2. Okay, so in an experiment, 0.9 moles of BrCl. So that's initially, we have 0.9 moles. This initially is before any dissociation has taken place. So you're going to have 0 and 0. Now your change, alright, you're going to have, because it is 2, it's going to be minus 2x. Here, you have no numbers in front of each of them, so it's just going to be plus x and plus x. And it says the amount of free chlorine in the mixture was found to be 0.4 moles. So that's the amount of chlorine you have at equilibrium. Okay, that is pretty clear, is your figure for x, because you're going from 0 to 0.4, so x is 0.4. Same here. Okay, here it's going to be 0.9 take away 2 by 0.4, which is 0.8. So at equilibrium you have 0.1 moles. Okay, that is not their concentration at equilibrium though. That's the amount of moles you have overall, but it's not their concentration, because in our question we have that it's a 5 litre vessel. Okay, so those figures now have to be divided by 5. So when we do that, we have BrCl going to be 0.02 molar. Okay, and the concentration of Br2, which is equal to the concentration of Cl2 as well, so they're both the same, that comes out to be 0.08 molar. If we want to find our Kc value, we're subbing into this formula up here. So that is going to be equal to 0.08 multiplied by 0.08 over 0.02 squared. And that gives you a final Kc value of 16.